Hi guys, today we're gonna see how to design a backchain behavior tree for drone pick and place missions. That is, drones like these, picking objects such as these first aid kits. And my name is Petter Ögren, I'm at KTH, the Royal Institute of Technology in Stockholm, Sweden. So first, what do we mean by a drone pick and place mission? Well, this is illustrated by the video here. So we have some drone like this hexacopter here. It's going to be controlled by a behavior tree that you can see on the right here, but we're going to get back to all the details. But just to illustrate the missions, we have the drone. It's picking stuff such as this kit here and then placing it at the destination, which in this case is the white cylinder here next to the tent. And after the mission is done, the drone is finishing by landing at the charging station over here. So that's a nominal mission. So let's see a mission where there's disturbances to the progression. So first we have a battery problem. So the drone goes before doing the pick and place, the drone goes to recharge here, and you can see the battery up here. And the recharging goes super fast just to save time for both you and me. So there we had a malfunction. That was the dip there. That was very quick. But it was some control reallocation was done to handle that. Now we're picking again. And now you see that the grasp is not as reliable as we would want it to be, but the drone goes to pick up the package when needed. It approaches the drop point here. And here we're actually going to disturb by moving the object off the point, and we can see the drone reacts by picking it up and placing it back in. And here the drone is actually going to drop the object, but by luck it lands in the proper place. So then the drone is happy and returns to the charging station over here again. So this is kind of the disturbances we want to handle in this mission. So just taking a step back, behavior trees are now in use in some different places. In the software provided by NVIDIA, their Isaac software, the software provided by Boston Dynamics used to control the Spot robot, in the ROS navigation functionality, and in the flow state introduced by Google's Intrinsic AI robotics company. And it was invented by computer game programmers some 20 years ago. So it's a nice modular hierarchical tool for putting together controllers or policies. Yes, that's it. So how does a behavior tree work? I think most of you know this, but just a quick recap. There are two fundamental composition nodes: the sequence that stops at the first child that returns failure or running. And you can read it as and. So here you want everything to succeed. So no stopping at failure and running. So you progress at succeed. So for instance, if you're holding the package, you want to make sure that succeeds, and then you go to make sure you're at the destination. And if that succeeds, you drop the package. And these three in sequence will get the package to the destination. Whereas this is a fallback, it stops at the first child that returns success. And you can read it as or. So here it checks, is the package at this destination? If we have a success there, we're happy. So either that, or if it's not at the destination, we go ahead and deliver the package, which is actually going to achieve this. So doing this, we're going to make sure this returns success. But that's a fallback. Or we could have other actions here that achieves this. So in this case, we're actually going to remove this guy. As you noted, delivering the package is actually what these three items in sequence do. So we can remove that and add this that does the same thing in a bit more detail. And just to illustrate the execution of a behavior tree, we have the ticks coming down and the success, running, and failure. Return status is going up. So if we have a tick at the top node here, we first check if the package is at the destination. If not, we have the OR functionality here. We will go into this subtree, and then we check, are we holding the package? Imagine we are, then success goes up. This is a sequence, so it wants success from all its children. So the next node is ticked. Make sure we're at the destination. Imagine we get running coming back here, then running progresses up the tree. If we don't get running, if we get at some point, we get success here as well. The sequence goes on to check the next child, and then running comes up the tree here, like that. And remember, this kind of happens all the time, so the ticks keeps coming back. So for some reason, all of a sudden, the package is at the destination, such as when the drone dropped it. This guy is going to start returning success, and then success goes up here, and we stop trying to get it there if all of a sudden it is there by some chance, or if we get help from some other agent working in the area. So note we're using reactive version of all nodes, reactive sequence, reactive fallback here. So if what I described here is not how you're used to the fallback and sequence working, then maybe you're used to the memory versions of these nodes, and then you need to check the difference, because the rest of the video is going to be confusing if you're not aware of this difference. So what about backchaining? Backchaining a BT is basically creating a bunch of small behavior trees, such as this. This is what we just saw. First, we check if the package is at the destination. If it's not, we do some actions to achieve that. We make sure we're holding it, we make sure we're at the destination, and then we drop it. And this can be seen, this is a special case of this general setup. We have some post condition here, which in this case is package at destination. Then we have an action down here that achieves it, dropping the package will get it to the destination. And then we have some preconditions for that actions. So before we can drop the package to get it to the destination, we need to hold the package and we need to be at the destination. When these two are satisfied, these two preconditions are satisfied, this action will achieve the post condition. So then we have the post condition, the action, and the precondition. And this is sometimes called a post condition precondition action BT, a PPA, because it's post pre-action. And it's also sometimes called a make sure, because we check something. If it's satisfied, we're happy. If not, we achieve it. So if someone kind of asks you to make sure the door is locked, you check that it's locked. If it's already locked, you're happy. If it's not locked, you lock it, and then you're happy. You might also have several different ways of achieving the post condition here. So you might add more actions with that post condition and then add their preconditions like this. So this is the general form, or you can add even more of these. So for a drone case, what does it look like? This is one example. This is another example of another part of the drone setup. So you check if we're holding the package. That's a post condition. The action to achieve that is you pick the package up, then you're holding it. And the precondition of this guy is you need to be at the grasp point. You can't pick the package if you're a kilometer away from it. That's another example of a PPA BT. Here's another example at the grasp point. That's a post condition. This is the action, fly to grasp point achieves that. And here you can actually, if you have no preconditions here, then the sequence with a single child is the same as just a child. So you can simplify this to just having the action, and then you get this little structure as a special case of this general thing here. The same thing with at destination. Either you're at the destination or you do an action to achieve it, fly to destination. So all these are PPA BTs, if you will. And the reason we're listing them here is that actually this is the subtree for holding the package, and it's right underneath, make sure we're holding the package. This is the subtree for flying to a destination, and it's right underneath, make sure we're at the destination. And this is the subtree for at grasp point, and it's right underneath, make sure at grasp point. So we're going to connect these in a backchaining way to get the entire tree in this way. This is the connection we just mentioned here. So let's see if we can just connect these. We get this big guy. So we merge the dashed nodes here. Or technically we're replacing the upper guy with the lower guy. So that's why this is a fallback node. But we're keeping the name of this action as a label for the subtree under here. So we replace these guys with a fallback, like here, but we keep the name of this guy as a label for this fallback, and the same thing down here. So this tree basically does the whole thingy here. These are normal fallbacks, but we have labels for them to make the tree more readable. So the label after the question mark is only for readability. It works like a normal fallback. So now this is what the kind of the backchaining thing is. We chain backwards to get an entire policy for achieving this, which is similar in spirit to backchaining as it's used in classical AI planning. So this was what is needed for the drone to get the package to the destination. But then you might ask, over a mission like this, are there any additional goals? We saw that the drone went back to recharge when needed, but it also went to recharge when the mission was complete. And there might be other things. So what are reasonable goals for such a mission? We want to avoid collisions, of course, because that's going to break our vehicle. We want to avoid no-fly zones. Maybe there's an airport nearby. Maybe there's a helicopter landing site. Maybe there's no-fly zones for other reasons. We want to avoid those. We also want to avoid running out of battery. And then we want to land when the mission is done. So we have some set of goals here that we're going to actually put in sequence. So the backchaining algorithm, it just doesn't backchain as we did to create this subtree. We list a set of top level goals, such as these, in a sequence, and then we pick each of these goals, and then we do backchaining to get a subtree like this. So listing these goals, then we do backchaining of those. So listing goals would be like this, maybe. First, we want to make sure the vehicle is okay. This is in terms of internal errors, such as propeller malfunctions and stuff. If the vehicle is okay, we want to make sure we're safe from collisions and no-fly zones. If that is satisfied, we want to make sure the battery level is okay. So if we're low on battery, we should recharge, fix the problem by recharging, and then worry about other things. Then we want to make sure the package is at the destination, and when all of these are satisfied, we want to go back and dock with the charger, waiting for the next mission. So we already saw the subtree of achieving this. That's the example we started with. If the package is at the destination, we're happy. If not, we make sure we're holding it, and we make sure we're at the drop point, and we drop it, and so on. So we have a check mark for that subtree. What about making sure the vehicle is okay? Well, first we can check if the vehicle is okay. So this is also kind of a PPA where we have several actions that achieve the vehicle okay. Well, in some general sense, I guess. First, if we have a propeller failure, if we have a hexacopter, like in this example, we can try controlled reallocation. We have a redundancy in the number of propellers, so we can fix problems like that. If that doesn't solve the problem, we might try an emergency landing to save the vehicle. If that doesn't work either, we might try an emergency ground impact in a safe area to avoid hurting other people. That is not really going to make the vehicle okay, but it's going to make the vehicle more okay than a dangerous crash. So, and this stuff is inspired by some papers here. Safe decision making for risk mitigation in unmanned aerial systems. That is kind of this part of the stuff. There's lots of details and interesting ideas here, but this is kind of a summary or inspired by that. And adaptive fault-tolerant control allocation for hexacopter systems is inspiration for this thingy. So basically, if you have a quadcopters with 4 propellers and one of them breaks, you're basically screwed. You just have 4 inputs, and you want to control pitch, yaw, and roll, as well as acceleration upwards. So you can't really do anything with just 3 propellers. But if you have 6 of them, you have a redundancy, and you can use that to handle some failures. You might want to check those details if you're interested. So just let's look at the next thing. Make sure it's safe from collisions and no-fly zones. So here we're just adding a simple tree here. We're not, obviously you can put a lot of work into the details here, but here we just we check if we're safe. If we're safe, we're happy. If not, we let this kind of action, avoid collision and no-fly zones, take care of everything. We're not going to get into details in this presentation about that kind of stuff. But if you're interested in collision avoidance in multi-agent systems, I suggest you look at this reciprocal velocity obstacle IDs presented by Vandenberg et al. So make sure the battery level is okay. We have a kind of larger subtree here that was also created using backchaining. And just to illustrate how that works, here we see that the top level, little PPA tree. If the battery level is okay, we're fine. If not, how do we fix the battery level? Well, we recharge. What is the precondition to recharging? We need to be docked with a charger. So the next level, PPA here, how do we make sure that we're docked with a charger? First we checked if we are. If we are, we're happy. If not, we need to dock, right? And there's two preconditions of docking. We need to be near the charger, and the charger needs to be free. If there's another drone already charging, we can't land on top of it. So what are the subtrees for achieving these? Well, how do we make sure we're near the charger? We fly to the charger, but we have to know where it is first. How do we make the charger free? We just wait until the charger is free, assuming the other drone is not broken or something. Waiting is going to make it free, and then we can go and charge. And finally, how do we locate the charger? If we know where it is, we're happy. If not, we can request an updated information if our old information was inaccurate, or we can do some search in a spiral pattern or whatever. So it's a bunch of these small make sure BTs on the PPA form, kind of post condition, action, precondition for this case, and so on, that are backchained to create the big tree, just as we saw with delivering the package. And we can also note here that actually making sure the battery level okay is a subtree, has a subtree that docks with the charger, and then we can use this at the end of the mission when we're done with all the pick and place operations, just to be back at the charger waiting for new tasks or missions. So just an observation here, when you do this design, you need to be aware of the dependencies you might have in your system. So for instance, when the idea is to achieve sub-goals in an order like this, there are going to be, or in many cases, there are going to be some dependencies. Like make sure we're outside no-fly zones, and then here we're flying to the charger in order to get near the charger. Obviously, flying to charger action, the fly to charger action here needs to be aware of the no-fly zones. I mean, if this guy is not aware of the no-fly zones, it's going to fly, it might fly into the no-fly zones, then this guy is going to kick in and fly us out of the no-fly zones, and then if the design is not good, this guy is going to kick in and fly us back into the no-fly zones, and so on. So this guy needs to be aware of this. So we want few dependencies in our design. That enables a modular design, which is what behavior trees are all about. But sometimes some dependents are really inherent in the problem, such as no-fly zones being having a dependency on every fly action we have in the tree. So yeah, fly to charger needs to be aware of no-fly zones. So we need to solve that, otherwise it's not going to work as expected. If you want more details on this, you can check some of our earlier videos on, for instance, 4 common bugs in backchain BTs, includes this guy, and BTs and controlled barrier functions, because controlled barrier functions is one way to address this problem. So the complete design might look like this. We have all the top level goals here. We have all the subtrees that we've discussed one by one. So this is how it looks. Now we have some added color coding here. So this is just to illustrate one instance in the execution where we're actually, the vehicle is okay. So green is returning success, red is returning failure, and yellow is running in this example. So the vehicle is okay, we're safe from no-fly zones, and then this guy is actually returning. We're doing search in spiral pattern to locate the charger. So just some comments on how to read a backchain behavior tree at runtime, so we can actually get a lot of information on what's going on if we use this backchain structure to design the BT. So the trick is just to read all the make sure labels, like these guys, along the running branch. So by the running branch, I mean you pick the running action and then you follow the all parent relations up to the root. That's what we call the running branch. And then you read the make sure labels here. So what are we doing when we're searching in spiral pattern? Well, we're basically searching in spiral pattern in order to locate the charger, in order to be near the charger, in order to dock with the charger, in order to make sure battery level is okay. If someone asks you what your agent is doing, you can just look at your tree and read the make sure labels to answer that question. And this is the exact same example. In the Unity simulation, we have the baby tree here on the right, and here the running branch is indicated by blue and not yellow, but green is success, red is failure. So we can read the make sure labels along the running branch, that is the blue stuff. So in this case, we're flying to the grass point to make sure we're at the grass point. To make sure we're holding the package. We don't have to read the sequence because they don't have labels. The fallbacks have labels. Make sure we're holding the package to make sure the package is at the destination. And the green stuff is already achieved. The vehicle is okay, the vehicle is safe, and the battery level is okay. And another example, when we're flying to the drop point, we're doing it to make sure we're at the drop point in order to get the package to the destination. And then again, reading the blue stuff from the bottom, we're flying to the drop point to make sure we're at the drop point, to make sure the package is at the destination. So a natural question might be, can we use the same drone? Now it kind of looks like a single vehicle application with a single package and a single destination. What if we have multiple packages with multiple destinations, and there's also multiple drones for achieving this kind of larger mission? Yes, we can use the exact same design, but we just add this node here, revise task assignment. So what do we mean by that? Well, basically, we've been talking about checking if the package is at the destination. So that's actually two kind of variables here. What the package is it this item or that item or some other item, and also what the destination of that package is. So if we have some code here that checks and that updates whatever we mean by package and whatever we mean by destination, we can have so packages here, for instance, the destination is the drop point, packages here, and kind of, so if we just update those two variables here, we can have the exact same design to solve multi-agent missions. So how do we kind of revise, how do we update these two variables? Obviously, you can do something more or less elaborate. So here I picked a fairly basic or very basic algorithm that basically checks a list of tasks, and then you pick the first package that is either not at the that is both not at the destination and not being carried by another vehicle. So you don't want to try to grab a package that another drone is already carrying, and you don't want to grab a package that is already sitting at its destination. But all the packages that are not being carried and not at the destination are basically up for grabs. And what you might realize that this is going to allow two different drones to kind of go for the same package as long as it's not being carried, which is obviously suboptimal. So if you want to do this in a more elaborate way, you want to solve some kind of multi-agent traveling salesman's problem, who goes where and handles what packages and so on. But this is kind of a basic thing. This is also probably what a human would do. I mean, if you're preparing a dinner party with some friends, you might want to, okay, I'm going to set the table here. So I'm going to go and get the plates, and then you meet some other dude who's already carrying the plates. Then you don't grab the plates from that person. You just note, okay, the plates are taken care of, and then you go for the cutlery or something. And most people don't solve TSP problems preparing dinner parties, but maybe some do. So this is what it looks like. Now we have two drones, one over here and the other guy coming from there. They're both first aiming for the same package, which is, I think, the yellow bag here. So this guy takes it, this guy picks another. Once this is grabbed, picks another. And now there's 4 these kind of first aid packages. We're disturbing this guy by inducing some drops here, so you need to pick it up. At the same time, the other guy is picking the green bag to this tent. Finally, we're going to allow him to deliver his package. So there's 2 more packages down to the right here. First, they're both going for the white one here, but once this is grabbed, this guy revises his allocation and goes for the red package. The white package is being dropped here, and the red is going to be dropped at the 4th tent. Obviously, to make this kind of faster, all the tents and all the packages are fairly close to make the video not being super long and overly boring. So when all packages are delivered, the rightmost goal is to be back at the charging station, and here we are at the charging stations. So that's the mission completed. So just a summary here. We did a design for pick and place of drones, multiple objects. The backchain design works well. I would say it can be extended to multi-agent missions fairly easily. You just need to add the revised task assignment module. The design is highly modular, but some dependencies are inherent in the problem, and you need to be aware of those, otherwise your design is not going to work as expected. So identify and deal with those. See separate videos on that. Thank you for watching. If you want to know more about behavior trees, there's a set of videos on YouTube. There's also a book that you might want to check out that is actually available for free on archive or not for free on Amazon. Thank you.